About to start our second lecture for the IMO showcase. So it is my great pleasure to have with us Diana Tolu from the University of California, Los Angeles. Actually, as you have seen, she is the first and only female instructor at this camp. So let's welcome her.
Thank you. Thank you very much. I hope all of you can hear me. So today I decided to discuss a geometry problem. And the problem we're going to discuss today is a problem from IMO 2013, which is problem number 3. All right, so let's see what the problem tells us. So you have a triangle, ABC, and you're going to consider the AX circle of the triangle. And you are interested in the tangency point with the side BC. So the AX circle intersects the side BC in a point that we're going to call A1. So let's draw it while we're presenting the statement of the problem. So we have our triangle, and we have a very classic point. We have the point of contact of the AX circle with the side BC. So it will be something like this, right? I'll make it nicer, because this is not tangent at all. Okay. Let's say something like this. All right. So here is the point A1. Okay, and we will also define the points B1 and C1. So B1 will be the point of contact of the BX circle with the side AC, and C1 will be the point of contact of the CX circle with the side AB. And the problem gives us a very interesting condition. So what the problem tells us is that we know that the circumcenter of the triangle A1, B1, C1 lies on the circle of the triangle ABC, lies on the circumcircle of ABC. So basically what's happening is that when you look at these 3 contact points of the X circles, the circumcenter is going to be on the circumcircle of ABC. And what the problem wants us to prove, so show that ABC, the triangle, has a right angle, has a 90-degree angle. So this problem is actually really cool. Think about it. You have the contact points of the X circles, and the only thing that you know is that the circumcenter of this triangle just lies on the circle of ABC. And using just this, you need to show that the triangle ABC has a right angle. All right? So this is what the problem tells us. Okay, let's discuss what should go through your head when you see this sort of problem, right? So what should be the basic steps that you should think about when you read the problem? First of all, the problem deals with the points of contact of the X circles with the sides. What do we know about them? Well, when we have a triangle and we take the contact points of the X circles, so like this will be our point A1. And let's call this point D and this point E. Well, every one of you should know the following. These two are equal, right? And actually, what's happening is that the length of BA1 is P minus C, where P is A plus B plus C over 2, and by C, I mean the length of the side AB. This is a well-known formula regarding the contact points of the X circle, okay? So this will be P minus C, and this will be P minus B, all right? So I'll also write that CA1 is P minus B. So basically right now, when you're going to take all of the contact points, you're going to have a B1 and a C1, right? And if I take C1 right here, and B1 should be somewhere around here, well, what's going to happen is that on the side AC, this will be P minus C and P minus A. And on this side, we are going to have P minus A and P minus B. So actually, when we are talking about the contact points of the X circles, we are going to have the following equal segments. We are going to have that BA1 equals AB1, that CB1 equals BC1, and that AC1 equals CA1. So this is the first observation. I think all of you already knew it, but it's going to be very helpful in the next step. All right, now we are thinking about the circumcenter of the triangle A1, B1, C1. By definition, the circumcenter is the intersection of the perpendicular bisectors of the sides. Okay, so we are actually interested in looking at the perpendicular bisectors of A1, B1, B1, C1, and C1, A1. And we know that when we draw these perpendicular bisectors, for example, B1, C1 is going to have a perpendicular bisector, one of the points where B1, C1 meets our circle has to be the circumcenter of A1, B1, C1. Why? Because the circumcenter lies on ABC. And where the perpendicular bisector of B1, C1 will intersect the circle is going to have to be the circumcenter of A1, B1, C1. So we are actually thinking, all right, it's going to have to be one of these 2 points, right? Either the one above or the one below. Okay, another observation to make is the following. I mean, the diagram is kind of weird right now, but what I want you to notice is that the circumcenter of A1, B1, C1 has to lie on the big circle. And the big circle is outside of the triangle. This happens if and only if we have an angle which is greater than 90 degrees, right? So one of these angles will have to be greater than 90 degrees. Let's assume without loss of generality that this angle is going to be greater than 90 degrees. So let us write this down. So since the circumcenter of the triangle A1, B1, C1 lies outside of the triangle, because again, the circle is outside of the triangle and the circumcenter has to lie on the circle, it follows that the triangle A1, B1, C1 has an angle which is strictly greater than 90 degrees. Okay, and we can assume without loss of generality, say that the angle A1, so B1, A1, C1, is strictly greater than 90 degrees. All right, so this angle is strictly greater than 90 degrees. What happens in this case is that the circumcenter is going to be above B1, C1, right? So the circumcenter is going to be actually this, right? When I intersect the perpendicular bisector of B1, C1, it will be the intersection above B1, C1 because your angle A1 is greater than 90 degrees. So the circumcenter will be somewhere around here. And we said we have two options, either this or this. So the only option that's left is the one above B1, C1, right? So from here, we can say, first of all, that it follows that the circumcenter of the triangle A1, B1, C1 lies, let's call it above B1, C1. Okay, and now we're going to make the key observation of the problem. So let us ignore most of anything that's given, and let's just look at the following diagram. We have our triangle, ABC, and we consider our points B1 and C1. From the first observation that we made, we know that these two segments are equal. So have that in mind, all right? And what I want you to do is consider the following intersection. We're going to take the intersection of the circle AB1C1 with the circle ABC. So we're also going to have this circle, and we're going to take this intersection. And we call it X. Okay, so what happens in this diagram, if you pay close attention, you have the circle ABC, B1, C1 are on the sides, and then you intersect the two circles again in X. So basically what's happening is that X is going to be the center of the spiral similarity that makes the triangles XBC1 similar to the triangle XCB1. If you don't want to talk about spiral similarity, obviously you can write it in a trivial way by just talking about angles, right? Angles in circles. Because what you have is that the angle right here is actually equal to the to half of the arc AX in the big circle, which is going to be equal to the angle right here, so ABX, which is actually C1BX. And also, what you have is that this angle right here is 180 minus ABX, but in the small AB1X, but in the small circle, AB1X is a C1X. And so basically, it is going to be equal to this one. So we obtain the same thing as in the spiral similarity. These two triangles are similar. But don't forget what we talked about in the very beginning of the problem. We know that BC1 and CB1 are equal. So actually, our similarity becomes a congruence, right? So we're going to obtain that the triangle XBC1 is congruent to the triangle XCB1. Okay, so what do we actually obtain? We obtain that XB equals XC and that XB1 equals XC1. That's actually great because first of all, look at what we obtain right here. XB1 equals XC1. It means that X, so let me write it here. So xb1 equals xc1 implies that x lies on the perpendicular bisector of the segment B1C1. But remember what we were talking about. So look at X and look at B1C1, right? We were talking about its perpendicular bisector. So its perpendicular bisector right here. We said, okay, we're taking the perpendicular bisector and it's going to intersect my circle in 2 points. A line intersects a circle in, 2 or 1 or 0 points. But in our case, it intersects our circle in 2 points. One above B1C1 and one below B1C1. But in our specific case, when I talk about the point X and with our assumption that the angle A1 is greater than 90 degrees, we established that the circumcenter of A1, B1, C1 will have to be the point above B1, C1 on the perpendicular bisector. So we are actually sure that this is going to be the circumcenter of A1, B1, C1. So now look at this point X. This point X is the point situated above the line B1, C1 that lies on the perpendicular bisector of the segment. So we actually obtain that X is the circumcenter of the triangle A1, B1, C1. But not only this, because we also obtain something very important here. We know that XB and XC are equal. And X lies on the circle ABC. So who is X? X is actually the midpoint of the arc BAC. Okay, so X is the midpoint of the arc BAC. It's right here, and it's the circumcenter of A1, B1, C1. And basically, this was the hardest part of the problem. Now let's finish the problem, and let's make a nicer diagram. So let's make BC the diameter. A is going to be right here. And we're going to have A1, C1, B1 right here, and C1. Okay. And we're going to have the midpoint of the arc, all right? I think, let's try to see how they're going to look, because I want you to actually see the angle change that we're going to make in the end. So let's say A1 is right here. And here you're going to put B1. Okay. And here is point X. So I will want us to take the midpoints of the other big arcs. So what's going to happen is that we're also going to take Y to be the midpoint of the arc ABC, and Z to be the midpoint of the other arc, of the big arc ACB. And think about it, the same way we obtained this congruence right here, in the same manner we're going to obtain that Y, which is the midpoint of the arc ABC, so if Y is right here, we're going to obtain that YA1 equals YC1. That Y is on the perpendicular bisector of A1, C1. And in a similar manner, we will obtain that ZA1 equals ZB1. It's the same spiral similarity, which becomes a spiral congruence. All right, so if we take the points as we were talking, X, and X, Y, and Z, which are the midpoints of the big arcs, and I draw XY and XZ. I mean, for XY, you can quite see it. For XZ, let's pretend. But what we know actually, because X lies on the perpendicular bisector of A1, B1. Why? Because X is the circumcenter, right? So, because X is the circumcenter of A1, B1, C1, we get that X lies on the perpendicular bisector of the segment A1, C1. But who else lies on that? Y. So basically, XY is the perpendicular bisector of A1, C1. And similarly, we're going to obtain that XZ is the perpendicular bisector of A1, B1. So that's about XY and XZ. And also, don't forget from the way we define the point X that AC1, B1, X is cyclic. So your angle A right here is going to be equal to the angle X right there. So we also have BAC, which we can read as B1AC1, equals B1XC1. All right, and now back to our angle chase. I was talking about the angle A. So our angle BAC, which we want to prove is 90 degrees, using the definition of X, it is going to be equal to the angle B1C1, B1XC1. And now I'm going to split this angle in two parts. And my first part is going to be B1XA1, and the second part is going to be C1XA1. All right, but don't forget that XY is the perpendicular bisector of A1, C1. So instead of the angle C1XA1, I can just write 2 times one of these angle. So basically, instead of the angle B1XA1, I can also write 2 times this small angle right here. So what we will obtain is that the angle B1XA1 is 2 times the angle A1XZ, plus the second angle is 2 times A1XY. So this sum is going to be 2 times the angle YXZ. And now we are almost done, because the angle YXZ is going to be half of this arc right here, right? It is half of the arc YZ. So when I multiply it by 2, 2 times of the angle YXZ equals the arc YZ. But don't forget who Y and Z were. They were defined to be the midpoints of the big arcs, right? So basically, instead of the arc YZ, I'm going to write the following. It's 360, the whole circle, minus the arc AY and minus the arc AZ. Okay, but Y is nothing but the midpoint of this big arc right here. So basically, the arc AY is half of the big arc ABC. So I can just write it as 360 minus the arc ABC over 2. And the same for AZ, because Z is the midpoint of the big arc, of the arc ACB. So this is minus the arc ACB over 2. All right, but instead of the big arc ABC, I will just move to the small arc. So I will just write 360 minus the small arc AC over 2. And then instead of the angle ACB, I will write 360 degrees minus the angle AB over 2. And now 360 is going to go away with the 180s from over 2. So what we obtain is that YZ equals, well, AC over 2 plus AB over 2. But who is the arc AC over 2? It is the angle B. It is the angle ABC. And AB over 2 is the angle ACB. So basically the arc YZ is the sum of the angles B and C in the triangle ABC. And this is 180 minus BAC. So look where we started from. We started from the angle BAC, which is the arc YZ. But as you can see, the arc YZ, if we compute it using the properties of the midpoints of the arcs, it is 180 minus BAC. So we obtain that BAC is 90 degrees. And our problem is done. Okay, I think this is it. This was my solution. If anyone has any questions, just raise your hand. Thank you for your attention.
Let's thank Diana for a wonderful talk. If you have any questions, please raise your hand. Any questions? Do you have questions? No? Okay.
Do we end up with an if and only if? And in that case, can we do it by proving that it works for a 90-degree triangle?
So you're asking that if you have a 90-degree triangle, then the circumcenter of A1, B1, C1 lies on the circle of ABC?
Yes.
I think so. I'm pretty sure of it. Yeah.
Other questions, please? Okay.
What's the motivation for the solution? Like,
Okay, so while I was presenting it, I tried to sort of build the intuition behind it. So as I was saying, when you take the circumcenter, you're going to need to look at the perpendicular bisector. And this configuration that we have right here on the third board, when you take the spiral similarity and you have this congruence of segments, actually the center of spiral similarity is going to lie on the perpendicular lines of both this segment and this segment. So if you have this configuration in mind and you know that the center of the spiral similarity lies on the perpendicular lines of both B1, C1, and BC, in your case, then because you are particularly interested in the perpendicular bisector when you build the circumcenter, then this is what brings you here to define this point X. Does it make sense? Yeah, okay.
Other questions? Do you have questions? Do you have questions? No? Other questions, please? No questions? All right. If there are no questions, let's thank Diana again.
Thank you. Thank you very much. Thank you.